At all costs, we are under the attack of an orbiting probe.
Notify all stations. Starfleet emergency, red alert.
Earth is on the edge of destruction.
We cannot survive unless a way can be found to respond to the probe.
The key to saving the future
Spock, you're talking about the end of every life on Earth.
can be found only in the past.
We're going to attempt time travel.
Sulu, take us home.
These are the voyages of the crew of the Starship Enterprise.
Judging by the pollution content of the atmosphere, I believe we have arrived at the latter half of the 20th century.
That was from Star Trek IV, Captain Kirk going back in time to save Earth. Again, that movie, they had to go back in time because the whales that didn't exist anymore, they were extinct, the humpback whales, had been communicating through long wavelengths through some probe out in deep space. Okay, so ridiculous concept, but interesting, and got me thinking. Whales communicate across thousands of miles through Earth's ocean. Could there be long wavelengths across Earth that are either receiving or possibility of transmitting signals? So interesting video. As always, thanks to my patrons. Love you guys. Thanks for all your support. If you want to become a patron and support the channel, go to patreon.com/Chris Lato. As always, just being here with an open mind is best form of support. Consider subscribing and liking the video if you do like this content. Now let's get to the video. Captain T. Kirk's venture into space and Star Trek IV actually got me thinking of these long wavelengths. Could it be possible? If you Google electromagnetic spectrum, these are the images that are gonna pop up, okay? So on all of these, basically ends here. This is a wavelength, okay? So as the wavelength gets longer and longer, it basically ends here. You can't find, it's very difficult to find any sort of diagram that goes lower than effectively 10 hertz or 10 cycles per second. Okay, challenge you to try and find something on the internet or at least on Google that goes below 10 hertz. I make the argument in my Dark Matter is Life video, you can review that here, that basically we just don't know what is going on at the low wavelengths. Okay, we just don't have the instruments to actually detect what's going on. You have to have a antenna as long as the wavelength of the wave to actually detect the whole wave. That thought went through my mind as I heard this interview between Lou Elizondo and Andy from That UFO podcast. Check it out.
From both Dan and myself. Now, we were talking and we've recently spoken to Avi Loeb and about the Galileo project, and we had a question, Lou, for you, that if you were Avi and his team at the project, is there a particular location and sensor system that you'd recommend to enable them to consistently observe these craft? And we put, for example, electroacoustic microphones tracking infrasound.
Yeah, that's a great way to do it. Infrasound is one certainly interesting potential. We use infrasound for other things as well. There's another way that is even simpler. In fact, it's absurdly simple. If I were to mention it, I think a lot of people have kind of that, a duh moment and say, "Wow, you're right. That's a pretty easy way to do it."
Infrasound. He mentions there. I don't know. Still don't know what the amazingly simple way to identify or at least get pointed out to these UAPs is. But infrasound, I started researching actually infrasound. It's quite interesting actually. So what is infrasound? Okay, so first, infrasound waves are defined as sub-audible sounds, pressure waves with frequencies ranging from the cutoff frequency of sound, 3.21 megahertz, to the lowest frequency of human audible band, 20 hertz. So that's 20 cycles per second. That's the lowest that humans can hear. Infrasound waves associated with large energy sources can propagate for several thousand kilometers or more along the Earth's surface. Therefore, infrasound waves can be effectively used for remote sensing of physical aspects of the Earth's atmosphere, compared to seismic waves in the same frequency range recorded by a broadband seismometer. There have been several reports of the production of infrasound waves by environmental sources such as volcanic eruptions, ocean waves, earthquakes, and the passage of aircraft. Also interesting, in addition, there have been reports of infrasound waves possibly generated by thunder, sprites, fireballs, meteorite falls, the re-entry of artificial vehicles, and auroral activities in the polar regions. This is actually taken from Science Direct. This is an article on the infrasound array observations East Antarctica. So infrasound waves can be created by aurora, by meteorites impacting the atmosphere, by earthquakes, ice sheets breaking off. So they're low frequency waves out there. This is where they sit, okay? This is 20 hertz, so below infra, below normal sound. And then you get to gravity waves, okay? I'll talk about these in a second, but these are not gravity waves like the electromagnetic spectrum. These are gravity waves like tides, okay? So pressure waves. The moon is actually, its gravity changes the tide. So that's what they're talking about here. But I will talk about gravity waves in a second. But this is actually infrasound. This is an interesting article. If we look at this actual station, okay, you want a large aperture. Like I mentioned, in order to capture these large wavelengths, we need very large system. We need a large detector, and that's really what this is. They space these detectors all around, okay? And this has an aperture alone of 20 kilometers.
The white dots that we see here are 60 infrasound stations. They monitor the globe for atmospheric or shallow underground nuclear explosions. Such explosions create infrasound waves, low-frequency waves inaudible to the human ear. This event here could be a volcanic eruption, a storm or an explosion, all creating infrasound waves that are registered by our infrasound stations. Such a station consists of several elements. This one has 8. The distance between the elements can vary from 1 to 3 kilometers.
So you have these pressure detectors, okay? So they basically have little barometers in there. And as this wave passes through, okay, it affects the pressure differently.
Types to an infrasound sensor called a microbarometer.
So this is how each little station detects the sensors. It's linked, and now you link several systems together in one big large detector.
Says again. Infrasound waves arrive at the station, are registered by the individual sensors, and transmitted as electrical signals via a radio connection to the central facility.
There you go, via a radio connection. The conclusions actually are pretty interesting. The established infrasound arrays in LHB clearly detected the temporal variation, frequency content, and propagation direction for microbaroms from the Southern Ocean. Moreover, several notable infrasound signals were recorded, including regional earthquakes, local signals with high frequency ranges, as well as the shock waves generated from the explosion of a meteoroid that entered the atmosphere in the northern hemisphere. So probably the most interesting to me is that a meteorite impacted on the northern hemisphere, and they were able to detect it with some reasonable accuracy in this station in Antarctica on the southern hemisphere. Okay, the problem with these infrasound detectors is these are very, very large waves, and so actually determining angle, okay, is going to be quite difficult. Okay, you need many sensors, like they mentioned. There's 60 stations around the globe. So we need to go to electromagnetic detection, okay, and that's what we need to move to, I believe. So how do we detect actually electromagnetic variations or long wavelengths? This infrasound detector actually reminds me of an interferometer. That's what was used to detect the first evidence of gravity waves in 2016 at the LIGO detector. So what is an interferometer?
Squeezing, Ray turned to a device called an interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
And you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected in the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
You're measuring gravity waves. And they did measure gravity waves at the Laser Interferometer Gravitational Wave Observatory, so LIGO. That was in 2016. Gravitational waves detected 100 years after Einstein's prediction. So this is LIGO. Basically, they had a super long interferometer like you just saw, okay? And that's what detected actual gravity waves in 2016 for the first time. Amazing. These are these long wavelength waves that we just now detected in 2016. So the question is, could there be more, much more information at those lower wavelengths that we just haven't detected yet or haven't learned about? This leads me into another interesting point, okay?
Why do you think they mutilate cattle?
That's a good question. I don't know. I don't know if they do.
I love that question.
The real answer to a lot of these is we don't know anything yet about these things. And we don't know if these things are all related.
Okay, sorry. What could be a reason they mutilate cattle? Let's say it like that.
Yeah, are they doing experiments? Are they collecting data? That's a good question.
Why cattle?
I don't know.
This is a very interesting interview between Kurt from Theories of Everything and Kevin Knuth, astrophysicist who has been researching into UAP. So Kurt asks, why are they mutilating cattle? And Kevin, he just has a speculation here.
Well, cattle are the most plentiful of all the animals, actually, by weight at least.
Yeah, I had an idea, and I'll share the idea with you. So this is, not even at the level of a hypothesis, right? This is just a thought. So Ray Stanford, who has studied UFOs in the 70s, refers to a sense of, he calls it euphoria, spelled UFORIA, euphoria.
Okay.
And he says that when you are near one of these craft, you have a feeling of euphoria. And he's recorded electromagnetic variations in the electromagnetic field from these things, and those variations happen around 12 hertz. So that's interesting because 12 hertz is close to the alpha rhythm frequencies that you get in the visual cortex when you close your eyes.
Okay, wait, sorry, I just want to make sure I'm understanding this.
So Kevin Knuth, what he's just mentioning here, okay, he's not saying it's a theory or anything, but basically this other guy, Stanford, has made the assertion that he can tell when a UFO or UAP is nearby because it emits some sort or interacts with the electromagnetic field at around 12 hertz. So 12 hertz, like we mentioned, 12 repetitions per second, which is, again, off the charts from what I just showed. This also corresponds to your brain waves, okay, to actual alpha brain waves. Alpha waves are one of 5 types of brain waves that we've detected at least. So delta, that's from 0.5 to 4 hertz. The lowest delta, which is the slowest, from 0.5 to 4 hertz is when you're in a deep state of dreamless sleep. Theta, those are from 4 to 8 hertz is when you're sleeping more lightly or when you're extremely relaxed. Alpha, okay, alpha waves, they're right in the middle of the brainwave spectrum, and your brain produces these when you're not focusing too hard on anything in particular, you're kind of relaxed. This is 8 to 12 hertz, so that's what Kevin was talking about. Beta, those are from 12 to 35, those are when you're wide awake, alert, and focused. And then gamma waves, those are the fastest at 35 hertz and above. Those are when you're actively involved in processing information and learning. So those 5 types. So what he says here is 12 hertz falls right in that range of your alpha brain waves. It's like your relaxing brain waves. This is just a postulation made by Stanford, but I thought it was interesting. Okay, so I went and looked. Listen, this is actually your alpha wave frequency. It's weird. I don't know if it's just in my mind, but I can I feel a little more relaxed when I listen to that. I don't know, just in my mind. Okay, so moving on can we use this to detect? Okay, so really, can we use these these low hertz, these low wavelengths, is there some way, infrasound, or like Lou mentioned, some other super easy way to detect these? And I was led to a magnetometer. That seemed like the easiest way, right? What's the simplest form of a magnetometer? Is a compass. Okay, so a magnetometer is a device that measures magnetic field or magnetic dipole moment. Some magnetometers measure the distance, strength, or relative change of a magnetic field at a particular location. A compass is one such device, one that measures the direction of an ambient magnetic field, in this case, the Earth's magnetic field. Okay, but there are hundreds, if not thousands, of different types of magnetometers. This is the longest Wikipedia page I've ever seen, actually. I mean, just look how many different types of magnetometers there is. I didn't know, I had no idea. They're used in laboratories, they're used in surveys, they're used in military. Okay, so let's go to military, that's my specialty. Okay, so magnetometers are used for defensive purposes. Navies use arrays of magnetometers laid across seafloors in strategic locations to monitor submarine activity. Look at this, even cooler, the Russian Alpha-class titanium submarines were designed and built at great expense to thwart such systems, as pure titanium is non-magnetic. I mean, that's crazy, right? The Russians made all titanium sub to try and thwart our magnetometers. Okay, military submarines, they're routinely degaussed, okay, pass through large underwater loops at regular intervals so that they can't be detected through magnetic anomaly detectors. Okay, so this is what basically we could consider is using a MAD. It's an instrument used to detect minute variations in Earth's magnetic field. Okay, so that's why they put it off the back of this, looks like a P-3 Orion, hunting for submarines. Okay, so get it as far away from the metal parts of the actual aircraft to try and look for these submarines. Very interesting. There's tons of different types of magnetometers. Could it be used to actually angle in on these guys? As far as spacecraft, okay, so that's the actual, what I'm looking to try and use it in. The first spacecraft to actually have a magnetometer was Sputnik, if you imagine that, right? It was also on Mariner 2 and Mariner 10. They also had magnetometers, okay, because you can actually look at you can measure the magnetic fields of other planets as well, okay, used in astronomy. So tons of uses for these magnetometers. So an interesting case where they're already using magnetometers in space is with SWARM. It's the ESA's magnetic field mission. So these are satellites, 3 satellites actually, that went up in 2013, okay, and they are actually monitoring the Earth, studying the Earth and its magnetic fields. I thought it was an interesting use case right here is the curious incident of swarm and sprites in the nighttime. So transient luminous events are optical phenomena that occur high up in the atmosphere, and they're linked to electrical activity and underlying thunderstorms. Okay, so they're very brief, lasting from less than a millisecond to 2 seconds and rarely seen from the ground. Okay, but if we look here, basically a paper published recently in Geophysical Research Letters describes how scientists from research centers in Poland use magnetic field data from swarm satellites and lightning observations from the geostationary lightning mapper and from the ground-based World Extremely Low Frequency Radiolocation Array to provide evidence of links between transient luminous events and magnetic field fluctuations in the upper ionosphere. So you can use these magnetometers to actually locate events, unexplained aerial phenomena maybe, in the atmosphere. But there are a few problems with this, okay? So there's a couple problems that I found. The first one is the Earth already has a magnetic field, okay? There's a lot of noise, if you will, magnetic noise in the environment. So one of the big problems though is that actually in order to detect magnetic fields, okay, the only way we know how to do it so far, because we haven't found a magnetic monopole, okay, is we use actually a magnetic dipole. You can watch my video on UAPs and nukes that I made. I explain more about the magnetic monopole and the magnetic dipole, okay? But basically, magnetic fields vary as a cube of the distance, inverse cube. Okay, whereas most electricity or electrical fields or light that I'm used to when we actually shoot a flashlight, for instance, the power of the transmission actually decreases at the inverse law. So following Coulomb's law, it's called Coulomb's inverse square law. Coulomb's law actually was very important. It was essential to the development of the theory of electromagnetism, maybe even its starting point, as it made it possible to discuss the quantity of electric charge in a meaningful way. This was in 1785 by French physicist Charles Augustin de Coulomb. Let's see what he looked like. There he is, holding that glass thingy. Okay, so what is the law and how does it apply here? So the law states that the magnitude of the electrostatic force of attraction or repulsion between 2 point charges is directly proportional to the product of the magnitudes of charges and inversely proportional to the square of the distance between them. So it's basically how strong are the charges, but then it's the square of the distance. Okay, so as you get further away, the power decreases by square. So it decreases very quickly, right? But not as quickly as if you are following the inverse cube law, okay? As we've seen with, it works with dipoles, okay? So inverse cube law, for both monopoles and dipoles, the field strength decreases as the distance from the source increases. So as you get further away, okay, from a monopole or a dipole, the power will decrease, okay? The field strength will actually decrease. As we see here, for point electric charges, the electric field strength follows Coulomb's law. It's proportional to 1 over r squared, often called the inverse square law. For electric dipoles now, so now we're talking about dipoles, the field strength decreases more rapidly with distance. And that's inverse cube law, okay? And since we've never found a magnetic monopole, okay, we have to go with the dipole. So look at this. Magnetic monopoles have never been observed, okay? So how do we actually mimic a magnetic monopole is we make the smallest dipole we possibly can. Again, I related in this last video on UAPs and nukes. So the point of this whole thing is the magnetic field, as far as we understand them right now, if it is a dipole, will be based on the cube, inverse cube. So the field strength of that magnetic field strength will decrease very rapidly, more rapidly than the inverse square law. But if we're actually looking for magnetic monopoles now, maybe this can be used to our advantage. Now, maybe if it is a magnetic monopole, it follows the same, I guess, same physics as the electric monopole, and maybe it's more powerful. Either way, not sure, but there is a lot of effects, there's a lot of noise in space, so this may be a factor. But spacecraft have had magnetometers for a very long time. Final point on this, why it could also be a factor, and an interesting point that I also learned was about superconductivity. Okay, so superconductivity is a set of physical properties observed in materials where electrical resistance and magnetic flux are expelled from the material. So I never knew this, but to get a superconducting material, yeah, you drop the electrical resistance to 0, okay? But you also drop all magnetic fields into that material also to 0. So it removes all magnetic fields now. I thought that was very interesting, and maybe that is a reason why this superconductivity was put into Pais's patents. It was one of the Navy patents built around creating these craft. So you can check that video out as well, where I go over Pais's 3 patents. All right, guys, that's it for this video. What do you think? Are there long waves out there that we don't know about? Could the Earth be communicating? Could our whales be talking to space probes out in space? That's just insane thoughts, but still fun to think about. I hope you learned something on this video. I learned a lot researching it. Thanks so much to my patrons. If you did like this video, please hit that like button. It shows me which direction to go on the channel, and I'll make more content like this. Consider subscribing as well. Have a great week, everybody. Take care. Peace.